For hundreds of thousands of years, humans have gazed at the night sky, wondering if they are alone in the universe. One bright light stands out among them all: the red planet, Mars. But even as telescopes, satellites, and technology confirm that it is a cold, inhospitable place, its attraction lingers. Today, Earth's inhabitants are spending massive resources to go there. But what will they find? A lone robot roams the surface of a desolate and hostile planet. It is the Curiosity rover of the United States Jet Propulsion Laboratory in California. It's the most powerful robot yet sent to explore the red planet. Curiosity's nuclear battery has kept it going for 5 years, as it has driven over 13 kilometers, sending back incredible images and data. It is one of the many high-tech spacecraft sent by humans to explore and map Mars in advance of a human landing. Mars is the second smallest planet in the solar system, and, when at its closest to Earth, 55 million kilometers away, 100 times the distance between the Earth and the Moon. It is the planet that perhaps most resembles the Earth, and for centuries there has been speculation that there is life, or was life, on Mars.
There's probably a magical mix of ingredients that have to come together to create life. And it definitely happened here on Earth, but it's not certain that it happened anywhere else in our solar system.
Our robotic system are our initial emissary to go to the new places, to learn more about the new places. But that's not the end. I think human wants to go beyond where we are. And I strongly believe that there is going to continue to be the ingenuity and the desire and the drive to go.
For me, we go to Mars because we want to hold up a mirror to ourselves. When we go to Mars, we learn things that really tell us about ourselves and about the Earth.
So why this burning desire to go to the red planet? And what might space explorers find when they get there? Technology is providing more clues than ever before. Here at NASA's Jet Propulsion Laboratory in Pasadena, California, scientists and engineers have been building satellites and rovers to explore the planet for decades, with the aim of giving humans the best chance of survival when they eventually go to find out if life forms exist there. Phuc Ly is head of the Mars Exploration Directorate.
When human explorers goes beyond the Earth-Moon system, the most logical place for the human explorer to go is Mars. Mars is reasonably close to Earth. From the studies that we have done, we are very sure that there is water ice on Mars that can become potential resources for the humans when they're on the surface of Mars. And obviously, it's a rocky, solid surface. They can set their foot down there. Even though it's cold, the atmosphere is very thin, it's still the most logical place for humans to go explore.
Mars may have been home to life forms in the past, and may still be today. Finding out if it could be home to humans, and whether there is or has been life on Mars, will also tell us more about our own planet.
I do feel that some of the ingredients are positive. We have now done radiation measurements from here to Mars and then on the surface of Mars. I mean, it's clearly there, the radiation, but it's perhaps a little bit more tolerant to human being. So I think there is still a lot to learn. There is still a knowledge gap as to exactly how the Martian material, how careful the human being has to be in interacting with those material.
The task of mapping Mars and bringing together all the information we know about the planet's physical resources, topography and geologic makeup falls to the United States Geological Survey Astrogeology Center in Flagstaff, Arizona. Heading it up is Laszlo Keste.
So there's actually a fleet of spacecraft around and on the surface of Mars. So at the moment we have the Curiosity rover, which is a large and nuclear-powered rover. We have, still living, the Opportunity rover, a much smaller solar-powered one. And then in orbit we have a European spacecraft, the Trace Gas Orbiter from ESA. We have an Indian spacecraft. We have 2 US spacecraft that are operational at the moment, and we use these spacecraft to talk to the rovers, but also to collect data from orbit about the surface.
The Curiosity rover flew for 55 million kilometers from Earth before landing in Gale crater. Landing on Mars is the most complicated aspect of exploring the red planet. The extremely thin atmosphere doesn't slow incoming objects, which have to use retroboosters, parachutes, and other means for braking. Leading the Curiosity command team is Lauren Edgar of the USGS.
We were all gathered in a room at the Jet Propulsion Laboratory, so all of the scientists were in one room, all of the engineers were in another room, and the engineers were the ones that were responsible for that crazy entry, descent, and landing. We used a sky crane, a brand new technology for getting this rover to Mars. I think there were plenty of people that were skeptical or wondering if this would actually happen, so there was a lot of anticipation. But as soon as we got the confirmation that we had landed successfully, the room erupted in cheers and everyone was taking pictures and really just enjoying those first moments.
I was a nervous wreck. I was sitting in the back row of that room. A lot of people were involved, and a lot of people put a lot of their several years of their hard life into ensuring that it's successful. As we go through the process and the thing succeeded in landing, everybody jumped up with joy, genuine joy, because I think it was just beyond exciting.
On the other side of the world, near the windswept beaches of Noordwijk, Netherlands, another Mars exploration project got off to a mixed start. Albert Haldeman and Pietro Baglioni worked together on the ExoMars project, a joint astrobiology program between the European Space Agency and the Russian agency Roscosmos. The first stage involved sending an orbiter and a lander to the red planet. The Schiaparelli lander crashed after it spun out of control during descent, confusing the guidance, navigation, and control system software on board. It was a lesson for all Mars explorers. The team plans to land a rover on Mars in 2020.
First of all, the Trace Gas Orbiter, TGO, is the biggest spacecraft ever launched to Mars. And that's just by itself. It also had a 600-kilogram entry, descent, and landing demonstrator module on top of it when it launched. We will take the lessons from the Schiaparelli lander that didn't succeed fully, but we got the data. In fact, we got telemetry all the way down to the ground, such as it is. And we are using that to make changes to the design we had for the lander that will carry the rover on its back.
Since the first probes landed on Mars in the 1970s, technology has come a long way. Today, rovers, orbiters, and satellites being sent to explore Mars have high-tech robotics and imaging capabilities. Engineers are still struggling to make landing on Mars safer and simpler for the machines, as well as, one day, for spacecraft carrying humans. Since the Curiosity rover successfully landed in Gale crater in 2013, it has sent back more than 200,000 spectacular, high-resolution photos of Mars, traveling 13 kilometers in the 5 years since it landed. It has 17 different mounted cameras and a drill to make shallow holes in the surface to test samples it gathers in the hope of answering the questions that scientists have always asked themselves about Mars. Was there liquid water once that might have been able to generate amino acids, the building blocks of life?
We basically spend a day on Earth planning what the rover is going to do that day on Mars. And then at the end of our day here, we uplink all of these commands as a bundle, send it to the rover. It tends to carry it out over our nighttime, and then we come back in the next morning to brand new data.
2 NASA rovers, Curiosity and Opportunity, are roaming the surface of Mars today. The Jet Propulsion Laboratory will be sending a lander, called InSight, in 2018. And the European Space Agency and Roscosmos will be sending the ExoMars rover in 2020. Here in the Mars yard of ESTEC, the European Space Research and Technology Centre, Albert Haldeman and Pietro Baglioni are discussing the next steps in the ExoMars project, an ambitious European-Russian plan to send a rover to search for signs of the biochemical building blocks of life. Albert Haldeman is the payload manager, also responsible for the assembly, integration and verification of the experiments on board.
The question of understanding, when we're looking if there was perhaps life now on Mars, or if there was ever life in Mars's past, is precisely to understand, are the building blocks sufficient, or are there some special circumstances required? And we're looking to see thereby whether Mars can teach us about ourselves.
The ExoMars rover is a third of the size of Curiosity and is designed to probe 2 meters below the Mars surface to search for the same compounds that combine together on Earth to produce amino acids. Pietro Baglioni is the rover manager.
The ExoMars rover is a machine that is about 300 kilograms. It's a compact structure provided with a solar array on the top to produce the required electrical energy, and inside contains a very sophisticated laboratory for scientific analysis.
MoMA is the Mars Organic Molecule Analyzer, so it's looking for organic molecules, that is carbon-containing organic chemicals, potentially biochemicals, but certainly organic molecules. We have indications, we have evidence that there's methane in the atmosphere of Mars. That's coming from somewhere, from some kind of chemistry. We know that meteorites that also fall on Mars, not just on Earth, but meteorites that fall on Earth contain polyaromatic hydrocarbons. Hydrocarbons are formed in interstellar space. It's falling on Mars, it should be there. It's not found and hasn't been found at the surface because the surface is very oxidizing due to ultraviolet radiation. We're going to look underground, and MoMA is sensitive to all of those things.
To search for life on the red planet, scientists must first and foremost be sure not to bring bacteria from Earth. Diana Margaritis is Director of Planetary Protection at Thales Alenia in Turin, Italy. She is responsible for enforcing the strict international procedures against cross-contamination between planets.
We are sending a spacecraft to Mars. So we have to avoid to contaminate Mars with terrestrial microbes. So we have to sterilize each piece of this spacecraft that will contact Mars, and then to integrate all these sterilized items in a very clean environment in order to avoid to recontaminate again these sterilized items.
The ExoMars rover is being built in a clean room, a controlled environment with minimal microbial contamination. Here in the Category 7 clean room, the ExoMars rover project manager Bruno Vinay is verifying the micromechanics that will be inserted into the Mars Organic Molecule Analyzer, or MoMA.
Since we are there to search for life, we have first to be sure of not bringing life from the Earth, but also to provide a very clean environment such that the possible detection of organics there is not contaminated by possible traces of organics that are present here on the Earth.
The tiny instruments contained in the mini MoMA laboratory, including 37 micro-ovens to heat the samples until they give off gases, will first be built and then disassembled to be reassembled in the cleanest glovebox unit in Europe. All the scientific instruments in the experiment are carefully sterilized using ultraviolet light, 95% proof isopropyl alcohol, and then heated in an oven for several days before being wrapped up and entering the sterile glove box. Anything that goes into the adjacent clean room, including camera equipment, must also be sterilized. Anyone entering must wear clean room garments.
Our requirement is 0 spore in the air and 0 spore in the surfaces. We have developed very strict procedures in order to avoid to recontaminate or to contaminate with the possible bacterial spores that are inside the ISO 7AC.
The carrier, that is the module that push the lander from Earth to Mars, will separate and will burn into the Martian atmosphere. So it has to respect some planetary protection requirement, but not at the same level of the parts that actually will land on Mars.
The key item on the ExoMars rover will be this 2-meter self-extending probe. It is built and mechanized at the production plant of Italy's aerospace conglomerate Leonardo at Nerviano, near Milan. Marco Molina is Chief Technical Officer at Leonardo Space.
We are in front of the real ExoMars drill. So the world-famous drill that for the first time ever will go down 2 meters under the Martian crust. And what we see here is a carbon fiber box. This has been already tested extensively for 3 months, entire 3 months, into a Mars-like environment. And this is the configuration in which the drill will be ready to go down into the Mars soil.
The 4 rods are assembled in a clean room, where they are housed in a half-meter-long box that is originally transported horizontally and then turned to the vertical.
At this point, we will need to provide the first extension rod able to be engaged with the drill tool. So we will have this carousel that is bringing the 3 extension rods plus a spare drill tool that is not going to be used, hopefully. So it will be rotating around this shaft, being positioned under the motor. The motor will start rotating, engaging with a screw, getting ready the first extension rod that is going then to be engaged into the drill tool, and then the drilling and moving operation will start again.
The diamond drill at the tip of the ExoMars probe will be able to collect and test tiny samples of Martian regolith from 2 meters below the surface. A tiny camera will photograph the subsurface of Mars, while samples are inserted into the MOMAR experiment.
A little piece like this is taken into the tip of the drill tool, and then with the opposite movement taken up through the 2 meters into the rover to be crushed and then analyzed into the lab.
So these samples, after being retrieved by the drill, are processed in the laboratory. So the first mechanism is used to transfer the sample from the drill to the internal of the rover. The second mechanism is used to crush the sample. Then the third mechanism is used to distribute this powder to a carousel that contains a refillable container and set places for small ovens. And then both the refillable container material and the material in the ovens are analyzed by the instruments that are installed in the laboratory.
In a room adjacent to where the Mars probe is being built, the ExoMars solar arrays are assembled and tested. A number of other instruments are also part of the mission.
So the ExoMars rover is kitted out with an exobiology payload. The set of instruments is organized in a way that a field geologist followed by a laboratory microbiologist would look at samples. There are a couple of instruments that are in the body of the rover that can look underground. There's a ground penetrating radar, and there's a neutron spectrometer that uses the background flux of cosmic radiation that scatters neutrons back into the detector. And what that's really sensitive to is water in the subsurface.
The goal of the ExoMars project is to search for recognizable signs of life, past or present, not only the planet's capacity to support it.
What would convince somebody would certainly be a smoking gun, seeing something in a microscope move that looked like a bacterium. We don't have instruments to do that, not only because we don't, well, primarily because we wouldn't expect to be so lucky or to find something like that, because the evidence doesn't suggest it's there. What we are going to look for with ExoMars, with our samples, is biomarkers, organic molecules, polyaromatic hydrocarbons.
NASA's InSight will actually launch into space in 2018.
Mars does have a thin atmosphere of mainly carbon dioxide. And one of the experiments that we're carrying on board of Mars 2020 is an experiment called MOXIE that will convert the carbon dioxide. It's a demonstration. It's not a big scale thing, but a technology demonstration of converting carbon dioxide into oxygen. And you can clearly imagine how the oxygen can be used. So if we can demonstrate that, that again improves our knowledge whether we can live on the resources that Mars provides.
Several of the new tasks to be performed involve science aimed at preparing for human habitation on Mars.
The rover, if you stand far away, looks a bit like Curiosity. In fact, probably more than 90% of the weight of the rover are made up of systems that are the same as what we did on Curiosity. However, the scientific instrumentations are quite different. You will also have this sample system that will acquire all this sample that will be put on tubes. And finally, we're going to try to land this system a little bit slightly better than before.
Rovers and orbiters are providing humans with much of the information they will need to actually live on Mars. But the first requirement is a good map. Laszlo Keste is one of the scientists compiling information from all the exploration units on the surface and orbiting Mars in order to fill in the gaps in our knowledge of its geology.
We collect images from the spacecraft in orbit as well as pictures from the rovers. In particular, Curiosity and the Mars Reconnaissance Orbiter, which has a camera on it which we call HiRISE. The HiRISE camera has a spatial resolution of about 25 centimeters per pixel. That doesn't mean you can see things that small. You can recognize things that are about a meter across. And the rovers are very easy to see in these images. And we can actually see the tracks of the rovers and figure out where the vehicles have been. And the combination of having the images from orbit and having the images from the rovers allows us to see and understand the surface much better than either one could do by themselves.
Mapping the terrain of Mars is done much like mapping terrain on Earth, using two stereo pictures at a time, like two eyes, in order to see in 3D and then convert the images into a topographic map.
It's amazingly fun to work with spacecraft that are exploring Mars. We do not understand the planet. We debatably understand how the Earth works. We really do not understand fundamentally how Mars works. One of the biggest surprises for me was realizing that there are lava flows that are geologically very young and that Mars is capable of having volcanic eruptions today. That was totally unexpected, and having the better cameras there and collecting more data has made that clear. And I'm sure there's plenty more surprises as we continue to explore.
Rovers, orbiters, and satellites began collecting images and data to be sent back to Earth. What they discovered was astounding.
The first spacecraft that flew by Mars was Mariner 4, and it basically flew by Mars. And frankly, the first set of data that we got back was showed that Mars is a very barren, very moon-like kind of a setup. But fortunately, then we followed by Mariner 9, And it turned out that we began to be able to see that Mars has a giant volcano. It's probably the biggest, tallest volcano in the solar system. It has vast canyons and vast channels. A lot of the thought at that time was that those channels are probably indicative of interaction with water, most likely in the ancient history of Mars.
The nuclear-powered rover Curiosity was designed to last just a few months, but has survived for more than 5 years on the red planet. Amazingly, the solar-powered rover Opportunity, which began operating on Mars in 2004, is also still roaming the planet.
We refer to this as the Mission Control Center. When we fly missions, we have to send commands to our missions to ask them to do certain things, and then we also relay those data that are collected by those missions back to Earth. And all these things are done through, for the deep space missions that we do through the so-called Deep Space Network. And a lot of the deep space probes are commanded through here. They construct the type of command that need to go up, and then would be then sent through the Deep Space Network to the spacecraft. And so this is kind of the nerve center of how we operate our spacecrafts.
The many remote sensing tools being used to explore Mars have greatly expanded our knowledge of the planet.
One of the most Mars-like places in the United States anyway is around here in Flagstaff, Arizona. We have the youngest significant impact crater, meteor crater. We have very nice volcanic fields. We have the Grand Canyon, which isn't as big as Valles Marineris, but it's still the biggest canyon we have available. There's very good places to go on Earth that look like Mars. Some of those places are in Tunisia and Iceland, and there are terrains there that you look around and it really feels like you're on Mars because you cannot see a plant anywhere around.
Mars rotates at a slightly slower speed than the Earth, and each Martian day, called a sol, is about 2% longer than an Earth day. Being further out from the Sun than Earth, its year is much longer.
So the seasons on Mars follow the same pattern as on Earth, but obviously the climate is more extreme and much colder on Mars. So during the summer at the equator, it actually comes up to a reasonably benign temperature. It approaches 30 degrees centigrade.
So when we first landed, we landed on ancient stream beds, so that was a great welcome to the red planet. We went there to find ancient habitable environments, and landing on stream beds was a good start. But then we only had to drive a short ways before we encountered our first ancient lake deposits. And not just was a lake present, but it had all of the right conditions necessary to support life. So the minerals that were present, were formed in neutral pH environment. So if you'd been there on the surface when that water was present, you would have been able to drink that water. We also found all of the building blocks necessary for life, and minerals that were in different states of oxidation that could have provided, an energy source for primitive life.
There is quite a bit of water on Mars, but most of it's frozen. There is ice, water ice, at the poles of Mars, and then underground it extends about halfway from the poles down to the equator. And we've recently discovered that some of this ice is in thick, clean slabs. So it's potentially useful because if it's relatively clean, we don't have to get all the rocks out of it to access it. What we don't know is the chemistry of that water. It could be contaminated with things that we would call pollutants.
Most of the planet is covered in what is called nanophase ferrous oxide. In other words, rust. As on Earth, the iron has been brought to the surface by volcanoes that produce a thick layer of basalt along with other minerals such as titanium and magnetite. When the rover Opportunity first photographed these tiny spheres, the scientific community imagined that they could be so-called iron oxide blueberries that are also found on Earth.
So there are things we call blueberries. You don't want to try eating them. They're hard little pieces of rock. They're actually very similar to BBs. They're small nuggets of iron-rich material. So what's happened is water has flowed through the rocks and the chemistry has changed and it's dropping out the iron that it picked up as it was flowing through the rocks. And once it finds a little spot where that starts, more and more of the material grows around there. And so we call these concretions. They just grow within the rock as water flows through it.
There is clearly water ice resources. And that is a key ingredient that I think Mars already provide. You know, when human explorers get there, it is something quite heavy. And if you don't have to carry it from Earth to Mars, it will help us a lot.
About 4 billion years ago, at the time the Earth was cooling, Mars lost most of its atmosphere. There is very low atmospheric pressure on the surface, and the remaining atmosphere is made up not of oxygen and nitrogen, but of a toxic carbon dioxide and nitrogen mix. The average pressure is about 1% of the Earth's, equivalent to the pressure found at 35 kilometers into the Earth's atmosphere, or the upper reaches of the stratosphere. What might have caused Mars to lose its atmosphere is still the subject of speculation. Could it have been the loss of the magnetic field and the slow cooling of the planet? Or a catastrophic event, such as the impact of a massive asteroid?
The atmosphere of Mars is very thin. It's about 1% of the Earth's atmosphere in terms of pressure. It's also predominantly carbon dioxide, so CO2. So it's not something people can breathe, but it's thick enough to blow sand around on the surface, have clouds. And one thing that's really interesting about that atmosphere is it gets cold enough that the CO2 will freeze out and it will form frost on the surface, and sometimes it will snow out of the atmosphere as well.
The Martian core is made up of iron, nickel, and sulfur. However, unlike the Earth's, it does not produce a magnetic field, which means that the surface is unprotected from solar radiation.
Mars today doesn't have an active magnetic field, but we see evidence in the rocks that it did have a magnetic field in the past. So there's certain minerals that lock in the magnetic field at the time they formed in lava flows. So early in Mars's history, it had a magnetic field that we presume protected its atmosphere and allowed it to be thicker many billions of years ago. As that magnetic field went away, the solar wind and other particles were able to hit the atmosphere and strip it away. And we have missions there watching how the thin atmosphere that Mars has today is continuing to be stripped away.
The planet is host to the elements which, it has been speculated, generated amino acids on Earth, some types of which combine together to form proteins. On Earth, these have been found concentrated around volcanoes that produce vital chemicals, high pressure, heat, and liquid water.
The basic structure of Mars is very similar to the Earth. There is an iron core inside, then a layer that geologists call a mantle around that, and then the crust on the outside where we can see the most recent activity. The mantle, we think, has gone relatively quiet compared to the Earth. It's not moving, convecting as much, but there's still hope for motion. We know that there is still some magma coming out of the mantle. So there is still some warmth in there, some heat, some energy to drive activity.
Mars is home to the most amazing volcanoes in the whole solar system.
The volcanic eruptions, along with the liquid rock, there's a significant amount of gas that comes out with them. The most common gas is going to be carbon dioxide. There'll be some water and sulfur compounds that come out. But sometimes you also get some methane. And that can be part of a volcanic eruption. You can also form methane by the heat of the volcanic intrusions, where the lava never comes out to the surface, so it remains magma, and that heat will cause chemical reactions in the rocks and produce methane that way.
The surface of the planet does show the presence of volcanoes, especially in the southwestern quarter known as the Tharsis Range. Here we find Mount Olympus, a massive shield volcano 3 times higher than Mount Everest.
The tallest volcano in the solar system is Olympus Mons. It's about 22 kilometers tall. The atmosphere is extremely thin at the top, but there's been relatively recent volcanic eruptions, so the surface is not very old for Mars. It's a few 100 million years old, which takes us back to about when the first dinosaurs were just evolving. That's about how young the most recent lava flows on Olympus Mons are.
The red planet is also covered by no less than 650,000 craters larger than 1 kilometer in diameter. This is evidence of the massive exposure to asteroids and meteorites that make it through the planet's thin atmosphere.
Asteroids can be a danger here on Earth. A very large one is presumed to have been the key reason why dinosaurs went extinct. Those kinds of impacts are very, very rare. But there are smaller ones that can still be devastating, can still damage a city and things like that. And those smaller asteroids are hard to find. They're small and they're dark. One of the best ways to study the population of smaller asteroids is to look at impact craters that are forming. And we can actually watch these relatively small impact craters forming on Mars.
As Mars exploration continues year after year, the wealth of knowledge expands, and the hope of sending humans grows with it. Researchers are eagerly awaiting the first photos from a unique mountain that sticks up out of the middle of Gale crater on Mars.
This is actually a very exciting time in the mission. We are currently perched on top of this ridge that's part of the lower part of Aeolus Mons, a ridge called Vera Rubin Ridge that prior to landing we'd identified this location as a really interesting spot because of the mineral signatures that we could identify from orbit. And so right now we get to investigate this hematite-bearing unit, and we're looking ahead into this clay-bearing unit and then into the layered sulfates. So right now we're right at that key transition and trying to figure out what environments might have been present and how did it change over time.
The complex geology of Mars and the hope that it might sustain life forms has turned the new space race into an epic and global odyssey for Martian hopefuls and scientists alike. But is it just wishful thinking? The next steps in the race to the red planet will involve doing more than exploring. Building a habitat on the planet will be the first phase in colonizing it.
Modern Mars is dry, it's very oxidizing, not capable of supporting life. But ancient Mars was a much different story. From looking at these ancient lake deposits and the thickness of that whole body of rock that's represented by ancient lakes, we can say that water was present there for hundreds of thousands to maybe 1 million or several million years. We have not seen any fossils yet. Of course, everyone's always hoping, you come in each morning to the new data and look at the new images that are down, and you're like, maybe we'll find that dinosaur bone.
The billions of dollars spent over the decades to find out as much as possible about Mars have given us some vital answers, raising the hope that human life is possible on the red planet. Possible, but certainly not comfortable. The mineral soil is toxic, the atmosphere is unbreathable, and water would evaporate once it reached the surface. Poisonous dust storms regularly cover the surface of the planet. But although they may be huge, they also blow over quickly.
In terms of the geology, so far we've seen evidence for ancient streams and deltas and lakes. We've seen both modern and ancient windblown sand dunes as well. Along with the geology, we're also doing all of this environmental monitoring to investigate kind of the modern surface environment. Wind speed and direction, temperature, relative humidity. current radiation environments, all things that will help prepare for future human exploration on Mars.
The dust storms on Mars are giant weather patterns that have winds strong enough to pick up dust off the surface. It's much finer grained than sand. It's probably best to think of it as like flour. It's very finely ground rock, and it gets picked up by these winds and carried very high. And when the weather is right, you could kind of think of it like a hurricane. If it's able to pick up enough of this material, it makes a giant storm that can cover most of the planet with this dust.
Any habitats would have to be covered with regolith, the Martian soil, to protect them from radiation, and multiple airlocks would be needed to ensure no toxic gases or minerals entered the living quarters. Agriculture would be entirely artificial.
So it's really hard for humans to survive on Mars for any length of time if we have to bring everything from Earth. So it's really important for us to learn how to live off the land, to find a way to make the soil less toxic, to be able to grow plants, to be able to make our own oxygen, to be able to make an atmosphere that we can breathe, at least within our habitats. Bringing anything from Earth is very expensive. It takes an enormous amount of energy. So it would be really helpful to not to have to bring things like bricks with us and be able to make that out of the materials that are there on Mars.
Efforts to get to Mars are likely to have a major payoff on Earth too. Producing radiation-proof spacesuits and habitats, conserving water and resources, and being able to manage contaminated soils are all technologies from the mission to Mars that could benefit Earth.
The challenges that we face trying to get people to Mars result in learning new technologies, developing new capabilities that can be helpful here on Earth. The ability to clean up toxic soils may be someday really important here on Earth, but the amount of recycling that's going to be needed for astronauts to be able to survive for a long period of time on a place like Mars is going to be technology that will be useful here on Earth.
Never before in the history of humanity have such resources been spent on exploration, nor has any such endeavor been undertaken by the whole global community working together. Mars will continue to attract investments for decades to come, as humanity reaps the benefits of research on Earth, and our will to discover and explore drives us further out across the frontiers of deep space.